Welcome to this lecture on network analysis. In this class, we will talk about integrating factors for differential equations. We have been talking about differential equations for the past few lectures. So let's consider a differential equation of the form so this equation is known as a non-homogeneous equation. Non-homogeneous equation where this term p is known as is a constant, and this q on the right hand side is a function of the independent variable time or it may be a constant. So this term on the right q is a function of the independent variable time or it's a constant. So in this equation, if I multiply both sides by a term e to the power pt, let's see what I get. I'll write e to the power pt, maybe use a different color, e to the power pt di by dt plus pi e to the power pt e to the power pt is equal to q e to the power pt. Okay, so what I've done, I have multiplied this equation. Let's call this equation number 1. I have multiplied this equation 1 by e to the power pt on both sides, and if you recall, we know that the derivative of a product of two terms is expressed as this form, right? And in this equation, if you say that x is the current I and y is this term e to the power pt, then d by dt of this term I e to the power pt, which is this term over here, if we take the derivative of this term, so what is this? This derivative I e to the power pt is actually equal to e to the power pt di by dt plus I e to the power pt I e to the power pt plus times p, sorry. So let's call this equation number 2 and let's call this equation number 3. Okay, so if you comparing equation 2 and 3, we see that this di e to the power pt over dt is actually q e to the power pt. That is the right hand side of equation number 2, right? Let's call this equation number 4. Okay, so what will we do next? I will now integrate this, and what will I get? I will get I e to the power pt is equal to an integral q e to the power pt dt plus some constant of integration k, and I'll call this equation 5. Now I'll do some more manipulation. I'll multiply both sides by e to the power minus pt. So what will I get? I'll get then equation 5 becomes I is equal to e to the power minus pt integral q e to the power pt dt plus k e to the power minus pt. This is equation number 6. So this is the general solution for the current, that is I. Okay, so we started off with this equation number 1, which is a non-homogeneous equation, and we ended up solving it, and we solved this equation and ended up with this equation number 6. Now the thing to note here is that there are two terms in this expression. Let me just I'll take them separately. This term, which is the integral term, this is known as the particular integral. You would have studied this in your differential equations course. And this term here is known as the complementary function. Okay, so the solution in general has two components, that is this particular integral and this is the complementary function. Okay, now if you take a look at the particular integral term, we find that the particular integral does not contain any arbitrary constant, and the complementary function, that is CF, it does not depend on the forcing function Q. So two things to note here: the particular integral, it does not have any arbitrary constants. It has only P and Q terms, where P is the constant of the circuit and Q is the forcing function. When we say there are no arbitrary constant, we mean that no unknown constant is present. All of the parameters present there are known. And the complementary function, it does not have the forcing function term, or the input term is not present there. So we will see in the examples that we solve later on that this P term, this is a positive constant, and it is determined by the network parameters. Okay, so, and this Q is the forcing function, or the derivative of the forcing function. This we'll also see when we solve some examples. All right, so these are the two sort of notes about these factors P and Q. Now in the limiting case, if we take the limit, in the limiting case, the complementary function must approach 0. What do we mean by that? Since I said P is positive, What is the complementary function? The complementary function is k e to the power minus pt. So the limiting value when t tends to infinity for this term, what does this tell you? Since this is p is positive and the exponential is decaying, so this term actually reduces to 0 in the limiting case. Let's call this equation number 7. And the value of I, that is the current, as time approaches infinity is given by I of infinity, which is equal to limit t tending to infinity, I of t is equal to limit t of infinity. If you take a look at this expression, this term goes to 0 when you have to see t is equal to infinity, and only this term will remain, right? So the value of I at t equal to infinity will be in effect the value of this term at t equal to infinity. Okay, so I will write it here. This is going to be e to the power minus pt integral q e to the power pt dt. I'll call this equation number 8. Okay, so from this we make another conclusion. When the particular integral pi does not approach 0, at t infinity, the value at t equal to infinity or t tending to infinity is said to be the steady state value. Okay, so when this term is a non-zero term, then the current is said to be non-zero at t is equal to infinity, and this value of current at t equal to infinity is said to be the steady state value, of the, sorry, I want to highlight this actually. This is the steady state value of the current, or whatever variable we are interested in that moment. Okay, now if you see this equation number 6, I will again take the help of this copy paste feature. I will copy this expression and I'll paste it here. Some things that I don't need. Okay, so if you take a look at this expression, I can then make another comment that I can say that I is actually a sum of the particular integral and the complementary function IC, where IP is the particular integral and IC is the complementary function. Or alternatively, I can write I is equal to ISS plus IT. Okay, so this is one expression. IP plus I is equal to IP plus IC, where IP is the particular integral, that is this term, and IC is this term, right? Or I is actually equal to the steady state term ISS plus IT, which is the transient term. So we'll make two quick notes here. This ISS is the steady state value and IT is the transient. Okay, so this is about the integrating factors. All right. So taking a look back, what have we basically done? We had a simple differential equation with us, which was a non-homogeneous differential equation. With the help of some algebraic manipulation, with the help of this factor e to the power pt, what have we basically done? We have sort of reduced this differential equation. We have simplified and solved this differential equation into this form, right? So these factors are known as the integrating factors. This factor e to the power pt is known as the integrating factor. So where is this useful? We'll see this with the help of an example. Let's draw a circuit. It's the same circuit which we discussed in one of the earlier classes. I'll redraw it here for you. Now in this case, what I want you to, if you recall, we have discussed this case in the class earlier. In the class, the case that we discussed, the switch was initially at 1 like this, right? And then we switched it over to like this at t is equal to 0, right? But now I want you to assume the reverse. What do I mean by that? I now want you to assume that initially the switch was like this, as in only the RL was connected and no source was present, okay, initially. And at t equal to 0, what is happening? The switch is being turned from 2 to 1. Okay, so I'm turning the switch from 0.2 to 0.1 like this. Okay, so in this case, what is happening? If you take a look, what is the circuit now? What is the circuit shape like? It is like this, right? The circuit is complete. This is actually complete, and the current will flow in the circuit. So if you draw the if you write the KVL expression for this, what will the expression be? It will be minus V plus Ri plus L di by dt equal to 0. Or we can also write this as di by dt plus R by L times I equal to V by L. Now if you compare this equation with the original equation that we had, if you go up and you compare this, I'll just copy it from here. If you take a look at this expression, what do you see? You see that this term P, what is this term? This term is actually R by L. And what is Q? Q is your V by L. Okay, and the other things are the same. So I want to remove this here. And I also want to shift this up. Okay, now if I talk about the solution for this equation, I will again go back to my original solution, which is this. Right, the solution for this kind of an equation is this. So if I put in the values, what can I say? I is equal to e to the power minus r by l t integral v by l e to the power r by l t dt, or plus k times e to the power minus r by l t. Okay, so this term is known as the general solution. Why is it known as the general solution? Because we don't know yet the factor k. K is still unknown. Okay. Now, how do we obtain the particular solution for this? We have to solve for this k. We need to obtain this k. To obtain this factor k, we can go back. We have to first solve this integral here. So how do we go about solving it? We take this I, and if you take a closer look at this expression, this term here, this term over here, the constants will come out, and the integral of e to the power x is e to the power x itself, right? So upon solving or simplifying this expression actually becomes v by r, and you are left with k e to the power minus r by l t. Okay, now how did this v by l get converted into v by r? You have to see when you are multiplying. I'll make a note here, e to the power x dx is e to the power x only, but when there's some other factor here also, then you have to go for the internal differentiation. So you have to keep this in mind. Okay, so this is the solution. I should correct myself here. The general solution is this expression. This is the general solution. Okay, now in the circuit which we discussed earlier, before switching, if you recall, what did I ask you to remember? Before switching, what was the circuit like? Before switching, the circuit was connected like this, right? So there was no source present. So what does that tell you about the initial conditions or initial current here before the switch was connected? As in when the switch was connected like this, what can you say about the current? The current is obviously zero because the source is not connected at all, right? So at the instant of switching, if you recall our discussions about inductors, we remember, you should all remember that before switching and after switching, the current in an inductor instantaneously does not change. So before switching action, before switching action, the current in the circuit is zero. The current in the circuit is zero. Current in the circuit is zero, and immediately after the switching, the current will continue to be zero. So I0 of 0 will be equal to 0, or the initial value of the current after switching would be 0. And the particular solution for this type of a problem, particular solution for this equation which we have here, this particular solution is going to be I is equal to v by r times 1 minus e to the power minus r by e to the power minus r by l times t. Okay, so this is the particular solution for this problem. Okay, Okay, so if you take a look at this the graph of this function, it is something like this. See, now there are two things that you have to keep in mind. We have this I, which is the ISS, this value. This is the ISS, right? And this is the expression for I. And let me show you the IT part also. This part is actually IT. Okay, so actually the waveform is this blue waveform. This is the actual evolution of current. So this waveform has two components. One is the ISS, okay, ISS, which is the steady state component. ISS, which is the steady state component, which we also can see from this term. This term, that is V by R times this term, which is independent of time. So this is the steady state part. So this is the orange part, and the other part, which is the transient part, happens because of this, right? This decaying exponential. So that is shown by this green graph. So what does this graph tell you? If you take a look at this graph, if you take a look at this graph, this blue graph here is the actual solution of the problem, actual evolution of the current. The orange line is the steady state value, and if you notice, the steady state value is achieved at time equal to 0 also. See, it is here always, right? Because it is independent of time. And what about the transient part? The transient part happens is this green. It starts here and then it goes on decaying like this. So what is the sum of these two? The sum of this steady state part, this orange, and this green, what is the sum? The sum is actually this rising exponential, this term, which is V by R times 1 minus e to the power minus R by L times t. So this is the solution of the particular solution of this problem, or this circuit, right? So I would want you to solve some more problems to get a better idea about this. We will also solve some more problems in the next class, but I want you to take a look at the book and solve some more examples. And you may have to watch this video another time just to understand how things are actually working, but this is a very interesting topic, and it should give you an idea about how the circuit is actually functioning. If I actually remove all of this, if I make a copy of this graph, if I make a copy of this graph and I paste it over here and I remove the extra terms, so what does it tell me? It tells me that the current is initially 0 and it rises till it reaches this steady state value like this. And this steady state value, what is the steady state value? It is this V by R. because 1 minus e to the power minus r by l t, this term goes to 0 as time goes to infinity. So this is the steady state value, ISS. Okay, so this is how the current is actually evolving. So I will stop here now, and I will see you in the next class. Thank you.